Hello, welcome to Basics of Finite Element Analysis Part 2. This is the beginning of 6th week of this course, and what we will do today and also in the remaining part of this week is work out a lot of details on how do we go around computing element level stiffness numbers and also element level values for force vector and q vector. So, that is what we plan to do today, and it is in continuation of the discussion which we had in the last week. In last week when we closed the discussion on FEA, we were discussing the shape functions for triangular elements. How do we calculate the interpolation functions for triangular elements? So, starting from today we will continue that discussion, and specifically today what we will do is we will actually work out an example for a triangular element and calculate the functions psi 1, psi 2 and psi 3. And once we are done with that and we get a better understanding of that through actually worked out example, then we will move to working out the details of a rectangular element, a 4-noded rectangular element. So, that is what the agenda is for this week. So, what we will do today is we will do an example for, so example involves calculation of psi I, which is a function of x and y, for a 3-noded triangular element. So, let us consider this triangle. So, this is node 1, this is node 2, this is node 3, and the coordinates of node 1 are 2 and 1, coordinates of node 2 are 5 and 3, and coordinates of node 3 are 3 and 4. Okay. So, for this specific triangle our aim is to find psi I. So, specifically we have to find psi 1, psi 2 and psi 3, and all of these are functions of x and y. Okay. Now, in earlier week we had said that the approximation this field variable u, it could be represented as C1 plus C2x plus C3y, and from this we had developed 3 equations that the value. So, u1, u2, u3 equals a matrix which we called as A matrix 1 x1 y1 1 x2 y2 1 x3 y3, right. And here x1 is the location of point 1 node 1, x2 y2 is the location of point 2 which is node 2, and x3 y3 are the coordinates of the third node. So, we had developed this expression. So, u1, u2, u3 is equal to, so this vector equals this square matrix times another vector C1, C2, C3, and from this equation we can compute C1, C2 and C3 in terms of u1, u2 and u3, and the relation which we had developed in the last week was this C1, C2, C3. So, let us say this is matrix A, then this is equal to A inverse U1, U2, U3. Okay. And we had actually calculated the value of this inverse. So, this is equal to 1 over 2 AE times these numbers alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2, and alpha 3, beta 3, gamma 3 times U1, U2, U3 like this. So, alpha I and here we had said, so these alphas are can be written in terms of x1, y1, x2, y2 and x3, y3, and the expressions for these are alpha I is equal to xj yk minus xk yj, beta I equals yj minus yk, and gamma I equals minus xj minus xk. So, this is what we had developed. Now, in this case we know that x1 y1 corresponds to 2 1, x2 y2 corresponds to 5 3, which is the second node, and x3 y3 equals 3 4. So, using these, so let us call this equation A, let us call this equation B, and let us call this equation C. So, using C and A, we can calculate all the values of alphas, betas and gammas. So, that is what we are going to do now. So, alpha 1, so alpha 1, so I equals 1, then j will be 2 and k will be 3. So, this will be alpha 1 equals x2 y3 minus x3 y2, and that equals 11. Similarly, alpha 2 equals x3 y1 minus x1 y2, and that if I do the calculation, it comes out to be minus 5, and then alpha 3, using the same type of a formula, we get its value to be 1. For beta 1 is y2 minus y3, and that works out to be minus 1. Beta 2 is y3 minus y2, and that comes out to be 3, and similarly I can calculate beta 3 as minus 2. And finally, gamma 1 is equal to minus x2 minus x3, and that is equal to minus 2. Gamma 2 equals minus x3 minus, oh I am sorry, this should be y1. So, this is, so gamma 2 equals x3 minus x1, negative of that, and that is equal to minus 1, and gamma 3 equals 3. And finally, so we have calculated alphas, betas and gammas, and AE equals alpha 1 plus alpha 2 plus alpha 3, and that equals 7. So, please note that AE is equal to area of this triangle, it is equal to the area of the triangle, and 2AE is the inverse of that determinant. So, these are our alphas and gammas. So, then we had said that psi I, which is a function of x and y, equals 1 over 2 AE alpha I plus beta I x plus gamma I y. So, psi 1, which is a function of x and y, which is associated with node 1, equals 1 over 7 11 minus x minus 2y, because this is equal to 1 over 2 AE alpha 1 plus beta 1 x plus gamma 1 y. Similarly, psi 2, which is the approximation function associated with the second node, this is equal to 1 over 7 minus 5 plus 3x minus y, and psi 3 xy equals 1 over 7 1 minus 2x plus 3y. Okay. So, this is how we can calculate psi functions for a triangular element. So, that is what we have shown. So, the next thing, so if we have a discretized system with a lot of triangles, then we have to program the computer in such a way that for each triangle we can compute psi functions, and then we use these psi functions and their derivatives to compute elements of K matrix and also the force vector. So, the next, so till so far we have been talking about a triangular element, a 3-noded triangular element. So, it is a linear triangular element. The next thing we will discuss is a linear 4-node element. And specifically, so a 4-node element could be a quadrilateral, but specifically what we will talk about here will be a rectangle. So, how does it look like? So, these are my global coordinates x and y, and I have a rectangle So, I have a rectangle node 1, node 2, node 3, node 4, and it is oriented in such a way that its sides are parallel to at least one of the axes, which is x and y. So, this is my x and y is my global coordinate system, and here I will also put a local coordinate system, which is x bar and y bar. X bar and y bar. So, to develop the interpolation functions for this rectangular element, in this case what we will do is we will use a local coordinate system to develop those. So, we will use local coordinate system to develop psi 1, psi 2, psi 3 and psi 4. Okay. So, UE can vary with, is a function of x and y, or if I am in local coordinate system, then it is a function of x bar and y bar. So, that equals a constant C1 plus C2 x bar plus C3 y bar plus C4 x bar y bar. And so, this is a linear expression, and like in case of a triangular element, I can also express u as a function of uj's, which are the field variable at specific nodes times approximation functions which depend on x bar and y bar, and my index of summation will be 1 to 4 in this case. Okay, it will be 1 to 4. So, our aim, like in the case of triangular element, is to find C1, C2, C3, C4 and also find out expressions for psi1, psi2, psi3 and psi4 as functions of x bar and y bar, which is the local coordinate. So, to do this, so before we start doing this, we will also put some dimensions on this rectangle. So, let us say the dimension of this rectangle is A in the along the horizontal axis, and this dimension is B. So, in the local coordinate system, the coordinates are 0, 0, it will be A 0, this will be A B, and these coordinates are 0 B. So, these are the 4 coordinates in the local coordinate system for the element. So, we write down expressions UE at 0 0. So, the value of this field variable unknown this field variable UE, it will be U1, right, because the contribution from all other nodes at the first node will be 0, and this equals. So, let us number these relations, let us call this equation 1 and let us call this equation 2. So, if I use equation 1, then at the first node, so this is node 1. So, for node 1, u is u1 and that equals C1 and C2 x bar, y bar and x are 0, x bar, y bar are 0. So, all the terms involving C2 and C3 do not exist, they vanish. Then for node 2, the value of u at A0 equals u2, and if I use equation 1, then this u2 equals C1 plus C2 times A. The terms involving C3 and C4 will not appear because y bar is 0 at node 2. So, this gives me C2 is equal to U2 minus U1 divided by A. Okay. This gives me C1 equals U1. Next we go to node 4. Okay. So, for node 4 UE, for node 4 the coordinates are 0 and B, and the value of U at node 4 is U4, and this equals C1, and at node 4 x bar is 0. So, C2 term will not exist and C4 term will not exist. So, what we get is C1 plus C3 times B. So, this gives me C3 equals U4 minus U1 divided by B. And finally, I do for node 3 UE AB equals U3, and this equals C1 plus C2A plus C3B plus C4 AB, and I have already calculated values of C1, C2, C3. So, from this I can calculate value of C4. I can calculate the value of C4. So, if I do the math, what I find out is C4 equals U3 minus U4 plus U1 minus U2 divided by AB. Okay. So, let us bracket these relations and call them 3. So, now what we do, so we have calculated the values of C1, C2, C3. So, this part of our aim is now completed. Now, the next aim is to find out the psi functions or the approximation functions. So, to do that, what we do is we put 3 into 1, okay, and then we get, so what do we get from that? So, UE xy equals, so C1 is equal to U1, so U1 plus C2 is U2 minus U1 divided by A, okay, plus C3 times y, and C3 is U4 minus U1 divided by B. So, it is U4 minus U1, and this should be x bar y bar divided by B plus C4 times xy. So, it is U3 minus U4 plus U1 minus U2 times x bar y bar divided by AB. So, now we are pretty close to getting the approximation functions. So, what we do is now we reorganize these terms. So, that is something which we will do in the next class. So, that is what I wanted to say today, and thanks a lot, and we look forward to seeing you tomorrow.